Airteam Institute's Introduction to Algorithms. In today's video, we are going to start by talking about trees, and in particular, we're going to be discussing binary trees. And we can think about trees as a natural kind of extension of our linked list. So if we had our picture of a linked list in mind from earlier, that would be, with a little reorganization maybe, be kind of an example of a tree, right, where we have kind of some nodes that are connected and we're kind of building stuff from there. That's kind of what we're going to be thinking about as far as trees are concerned in this video lecture today. So, what is a tree? It's probably easiest always to see this by example, right? So here we have kind of a portion of a tree, kind of maybe describing HTML a little bit. So this is kind of an HTML document tree kind of here. We have our kind of body, which would be kind of our main place we would be putting content. Maybe some portions of that content could be an unordered list, and that could have some members or elements inside of that, right? We might have a heading, we might have a second heading, right? Different things like that as well. So these would be kind of ways we could organize things in terms of this tree. Now, one of the things to kind of stress is we really are going to think about these things recursively throughout a lot of today. So will be helpful to think of many things recursively when we're talking about trees and operations of trees and things like that as well. So we'll review some of this kind of vocabulary there as well on the next couple of slides. But we kind of start with our root. This is kind of the bottom of the tree. There's all kinds of arguments, right? Should our trees grow up? Should our trees grow down? Typically, even if we're calling this the root, we're going to kind of go down on the page when we're talking about this. Officially, though, there's no kind of up or down, right? There's farther away from the root and things like that. So this is going to be slightly different than kind of what we were just highlighting here. But let me kind of just stress our kind of recursive definition is we have a root and then we have some subtrees from there, right? So these might be of different sizes, right? In this case, we have kind of a pretty small one here in the middle there. Let me just differentiate all of the colors here. Right, so we have these kind of three different subtrees in this case. And right, we would have edges that are connecting these things. So in this case, we have our root, then we have kind of three edges connecting them to these three kind of subtrees from there. Right, we'll talk about some of these other things like parent, child, siblings on the next couple slides. But right, recursively, we kind of have a root, and then we have subtrees kind of pointing from that root by edges, right? So all of these things, it's going to be helpful to think of these as kind of more subtrees there as well. And as far as these operations are concerned, right, we do want to think of the three pieces as subtrees, right? So this one does have a first, a second, and a third subtree, right? So the edge here, of course, it can point to that single node or things like that, but we kind of want to view it, and this is going to come up in our implementations as well. We really want to view these as kind of subtrees themselves. So even if there's a single kind of node in the subtree, right, that could still be thought of as kind of a subtree with just a root, right? Just a root is a fine, small tree as far as things we're thinking about as well. And so It's slightly different than the idea of a linked list, but it's kind of very similar to those types of things. We still, though, have kind of set directions and stuff like that here. So just to be kind of careful and kind of stress some stuff here, right? Edge like this is not allowed, right? So because we have subtrees always, right? There's no loops, etc. So there's none of this kind of funny business that can kind of happen in more general structures like this. But everything has a kind of set level, right? Once you go to the root, you go from that parent to the children, right? So things kind of work in this way. So I've said enough about some of these words, right? Let's kind of just go through and kind of talk about these as well. So all of our little circles here are nodes, right? So we have all of the different nodes in the tree. These nodes or these kind of parents are kind of connected to our subtrees via these kind of edges, right? So as far as visualizing this, right, these kind of connect our different nodes, or if you like, connect our kind of root to the subtrees, all of those things like that as well. We pretty much mentioned this before, right? The root node is the unique node with no incoming edges, right? So any other node in this tree will have incoming edges. Why are we kind of defining it this way? Well, remember, these could be ordered in different ways, right? This doesn't have to flow downward, right? Maybe the body is in the center and we have all these edges kind of going outward, right? Even if this is mixed up, the root is still unique in this case, right? There is only one of these that we're going to have, and everything needs to be kind of connected to it or connected to something that's connected to it, right? Stuff like that as well. Now, as we string together some of the edges, right? Multiple edges or a single edge or things like that. That's where this idea of a path comes in. So here, right, how does this help us talk about things then? Well, like I was just saying, the root node is the one with no incoming edges. Any other node has a path from the root node, right? So any other node, we can follow some of these edges and it will connect us to one of those nodes there. In fact, it has to be a unique path, right? Again, because we have subtree, 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 we have this recursive subtree structure, any of these paths are going to need to be unique, right? There's only one way to get from the root node to one of these other nodes in the tree in this case. So some of these things you're just going to get comfortable with. We can come back to them, of course, as we're kind of using them more and more. But I just want to make sure they're all here so we have a place that we can reference them if need be as well. Remember, I've been stressing that everything has kind of this nice direction, right? Because we have our root node at the top and then kind of connections from there as well. So because we have these directions, right, you want to kind of think of these things in terms of a family tree, right? So much of this vocabulary here would match the kind of wordings you'd use for a family kind of tree, right? So if we have a parent, then the nodes connected to that node are the children, right? So in kind of a set here, we could have kind of this node right here, the unordered list node is the parent in that example, right? And then we would have two children of that being the two specific list elements or something here, right? That doesn't need to be, right? Every node isn't a child or a parent, right? Things like that as well, right? We could just have easily moved this over to the other side. Now we have another parent and child. We could move this up to our root node, right? Now we need to add a couple children. Here we have a single parent and 3 children, right? We always have one parent and then possibly multiple childs from that parent in each case. Now, we're not going to stress these as much, but right, when I'm talking about this vocabulary for like family trees, I do mean that, right? So I'm not going to have it officially on the slide, but these 3 children here, highlighted in our diagram in green, would be referred to as siblings, right? They have the same parent, so they are all siblings, right? We might consider all of these nodes in the entire tree, right, outside of the root as like descendants, or sometimes you'll hear ancestors, right? So those aren't as kind of official, but those types of wordings can be helpful for understanding the structure and organization of our tree in this case. So this is kind of our family tree slide vocabulary, right? We do have some kind of ones here where we're talking about lengths, and there's some more kind of tree analogies here as well. So for example, if we are talking about leaves, so a leaf node is a node that has no children. So one thing to be cautioned of here, they don't have to be kind of in the same position or something. They can be kind of spread out, right? Anytime we have, in a sense, a dead end, this is a leaf of the tree. Now, we can count these things in levels as well. So as far as levels, we have kind of like the root is at level 0. So one thing to be careful of in our definition here is that, right, we are doing this similar to how we would index a list, right? So our first level here is level 0. Then we would have kind of level 1, and so on and so forth. Right, so that would be level 1, all of those nodes in that kind of list there. And then at the bottom, we have level 2 in this case. So any of those across, right, this is level 0, this is level 1, this is level 2. So the height is the maximum level, right? So in this case, the height of our diagram would, of course, be 3. So here, the height is, sorry, not 3, 2, right? Because that is our maximum level here. So that's kind of a common thing to be a little bit careful with. These are kind of distances from the root. So the root is like 0, level 1, 2. So this tree has a height of 2 in our example we have here. Okay, so we have kind of a general definition of a tree, right? So you might have your node, you have the children of the node, kind of stuff like that there. Now, what are some difficulties of this? Well, we might have to keep track of how many children there are, right? We have like a first, second, third child in some of these cases, right? Maybe we want to limit that, maybe not. As far as we're concerned, we do want to focus on a special case. So this will allow us to kind of easily work with some stuff, but also be able to talk concretely about some operations and stuff from there. So our focus, as you can guess from the title today, right, in parentheses here, we had binary trees. Our real focus is going to be a binary tree in this case. So what is the help here? Why is looking at a binary tree going to be helpful? Because now, right, if we restrict the number of children, right, each parent has at most 2 children, we can then specifically talk about them. right? We can talk about left, right? If a node has a left child, right? And then right. So we have two of them. We can mention them by name. Is there a left one? Is there a right one? Maybe we want to change the left one, change the right one, add something to the left, or delete something from the right. You know, we have specific things to talk about here. We don't have to always worry about doing loops, right? You don't have to loop through the possible children. You don't know how many there are, right? Those are some of the stuff you kind of want to be talking about and thinking about in this case. So we're not going to do an official abstract data type. That will be coming in kind of the next video for kind of a specific application of this. But as of now, we do want to practice some different things we can do with binary trees, right? So we of course want to create a new binary tree. Now, I want to make a note of this here. So as I'm kind of thinking here, see if there's something, try to understand yourself what's different about our kind of creating a new binary tree in this case than we might normally have, right? So note, right, the tree always has a root. So this is different. Everything we did in the past kind of abstract data types, right? You created an empty list. You created an empty stack. You created an empty linked list even, right? An empty map. Here though, it always has a root. So when we create a new binary tree, we have a given root value in this case. Now, what are our kind of operations? We're going to insert a node on the left, insert a node on the right, and right, we might want to get the left child, get the right child, and maybe change or set, kind of get the root value here as well. So notice, right, the tree kind of has a very, very special place for the root. If we're talking about changing the values, right, or talking about getting the values, right, we only have those operations for the root. Why is that? Because we can always think of these recursively, right? So for example, right, if you want to get the value of the left child, right? So for example, right, only work with the root. And so kind of if you want to do other stuff here, right? So for example, to get the value of the left child, right? What can you do though, right? You can do this kind of using our recursive structure here. So, right, we want to first get the left child, right? So we would kind of do get left child, which does what? This returns that left child, thought of as a subtree, right? So this is something we need to be careful about when we're building this. We're going to do an implementation quick in a second. We're always thinking recursively. We always want to think of this left child as a subtree. So when we call get left child, of course, this would be on our object, right? So if we had a binary tree B, I'm omitting the B dot get left child or something here, right? And then from that point, we could get the value, right? So dot, that's its own object. On that object, we can call get root value, right? So that would be the way you kind of get the value of the left child in this case. Now, there's another thing here that's a little bit ambiguous that we haven't really talked about the details of, and that would be this insert a new node. So this is one here that we want to kind of talk about, and I think it's easiest to do this if we're kind of talking about the example on the kind of next page there as well. Right, so we want to kind of think about what does it mean to insert a new node in some case. Okay, so let's just though kind of look at some of our examples in this case, right? So now we're kind of looking at, okay, we're building this binary tree. What is the picture of this binary tree going to kind of look like and stuff like that as well, right? So this is where some of the things we need to kind of be worrying about are kind of relevant and things like that too. So at least the very, very basics are okay, right? So the very, very basics should be fine here, right? So if we want to kind of initialize a tree, right? So if B is equal to our binary tree with the letter B here, right? Remember, this is creating a new tree with a root value of B. So this kind of is all pretty straightforward as far as kind of building up our tree from there, right? And so nothing's done. There's no left, there's no right, right? We'll talk about how you implement that in a little bit here. But then, right, for example, we could build up the tree kind of from here. So what if we call b.insert left and we put the kind of value a there? Now all of a sudden we're drawing kind of a new node, right? Or really a new subtree, right? So remember, we want to think about this as its own subtree. To the left side now, we have a value of a. Now, what about if we do the same thing on the right? So b.insert right, kind of c. We will put kind of a c on that side as well. So everything's kind of repeated in this case there. Now, none of this should be shocking, right? I'm not going to really worry about, right, now if we call b dot get left, right, we'll get a, right, b dot get the root value, we'll get b, b dot get right, we'll get the kind of c value, or we'll get the node associated with that, right? So remember, we're not actually getting those values, we're getting those subtrees. But the real question here is, okay, what happens if we now look at inserting again in one of these sides? So what if we b.insert right d? Or let me just do r, just because this is going to be kind of way different now than maybe we're kind of going to be thinking about in this case. So what is different at this point, right? What's different here is that we already have a right subtree, right? At the moment, this little tree over here is our kind of right subtree in this case. So that's kind of what's happening here. Now, we would like to, right, keep our C on this side. So the C kind of needs to get moved down though. This is where the insert right comes in. So if we insert on the right, we're going to say, okay, R goes here. It's a new node in this case as well. And we'll talk about this a little bit more in a second here as well. This is going to be the right child of R will be that original C we had in this case. So when we're inserting on the right, kind of everything is shifting to the right in that case. Could you do this differently? Yes, but right, I'm doing this that will in a way that will match our implementation as a way of kind of thinking about this as well. If you do this on the left, it shouldn't surprise you, hopefully, that again, the A is going to get shifted down. So we have kind of something there. And then the L goes in here, and this is again pointing to the left. So we kind of preserve the kind of left in this case as well. So that's kind of what's happening here. Now, one thing I want to mention, as far as B is concerned, if we're thinking about binary tree there, right? Suppose we want to add a node here, right? Suppose we want to add D as the kind of right child of L. Can we do this with like a direct command from B? No, right? This is again where the recursion comes in. We need to be talking about, right? Okay, the children we can use and stuff like that as well. So how to insert D here. So how do we kind of go about doing that? Well, first of all, we need to be talking about the left child, right? So we need to talk about that left subtree. So our first step here is, and I guess let me just match this in red so we kind of have that as well, right? We're going to first need to kind of get that value, right? So we get the left child. So now at this point, instead of working with B, we're working with the node or the subtree starting with L, right? So I'll erase this in a second, but as soon as we call this command, we're kind of in this subtree right here, right? We're in this little smaller now tree in this case as what we're kind of working with there. And then at that point, we can add our right child, right? So now we do dot insert right. This is now empty, right? There's no node there currently. And we can insert kind of a D in this case there. So these are some of the kind of things we can do where we're talking about kind of adding or inserting values and stuff as well. So remember, for kind of insert left and insert right, these are kind of shifting nodes down, right? If we kind of need to. I'll review this again when we're talking about the implementation here, but it is important to remember or use that word insert. Insert left is not just like set the left, right? We didn't say the setting the left child or something. We are inserting a node kind of in that way. Okay, so as far as implementations go, we know that kind of working with our links, working with a linked list and stuff can be a little bit tricky sometimes, but actually it simplifies stuff when we're talking about a tree because this really matches, right? Our drawing, my diagram of the tree kind of automatically thought of this as nodes that point to other things, right? So everything kind of works out pretty nicely here. So let's do kind of the easy ones first. So we initialize our tree. If we're talking about initializing, right, we have kind of three main pieces of information we're going to be looking at, right? We have our key. So the key here is like the value in a sense, right? So what is the data associated with that node, with the root? So every tree we have a root with kind of a root object, that key there. And then it's empty in the sense that there is no left child and no right child. Now, one of the things I kind of want to mention here, right? You might have thought when we're thinking about this, right? That we would have like a node class that we would use here or something like that. Note, right? We do not actually have a separate node class here, right? It's all recursive subtrees in a sense, right? So there's no extra node class, right? Actually, as the binary tree, right, you store the root value and these kind of two pointers. That's what the tree itself is, right? You point to the left child, right child, and you have a value. You don't like create a node like we did for a linked list. Everything's in the binary tree class itself. So we have our getters pretty easily, right? If you want to get the right child, you return the right child. If you want to get the left child, you return the left child. I know I've said this a bunch, but let me just kind of caution us one final time with the implementation, right? So remember, this is returning subtrees, not values or something like this. So if we want to talk about values, you need to do something else. These are returning those subtrees there. And then, like I mentioned, everything is kind of done according to the root, right? So if you want to set the root value, notice we are allowing for this value to be changed, right? So you can change the value stored by the root. You can get the value that's kind of being stored currently as the root kind of there as well. So again, recursively then, our interesting kind of topic was the insertion. So what if we insert left? What if we insert right? So as far as those are concerned, what are the easy cases? Remember, the easy case is when there's nothing overwritten, right? So if nothing's overwritten, nothing kind of is there for kind of an issue. So just to highlight the beginning portions of these, right? If there's no left child, you just create a new left child. Again, it's a kind of sub-tree. So you create a new binary tree, right, with the value you're looking for. If the right side is empty, if we're trying to create a right child and everything's empty, we just create a new one, right? We create that new node and that new binary tree in that case. So always subtrees, right? So here, this really highlights the recursive nature. Every single time we're creating a new binary tree as this child. Now, what happens if we're doing the insertion, right? Well, here again, new binary tree is created, right, in both cases. But then we have to kind of keep the information we have there so far and keep it stored. So remember we said if we insert on the left, right? So we have kind of our root value here, our R, we're kind of having an L here as our original kind of left, right? If we are inserting kind of a new value from there, right? So what happens if we're inserting a new value in this case? Well, we first of all kind of just create a new binary tree, right? So let me just use n here for new. Now, that is our kind of new binary tree in this case. Let me kind of move this L down here a little bit more extended just so we can kind of work this way. So we have our new node here. At the beginning, it's connected to nothing. But then we set the left child of that, right? T.left child. We now set that to the self.left child. So it's pointing to the root's left child there. And then, right, we set the left child of the root, right, our self, the original binary tree, to our value there. So now at this point, after we have the link to the left side, we are kind of shifting this over this way then as well. And our kind of new left child of the root is going to be pointing to the new node in this case. So everything is kind of similar on the right side, except everything gets pushed to the right in that case there as well. So especially with the implementation given, right, you should be able to kind of step through these piece by piece and hopefully kind of understand what's going on and what's kind of happening in these cases. We'll do more complicated implementations of this in the next video. or kind of talk about them a little bit more that way. But that will be slightly different kind of procedures here. We're still going to be using this binary tree implementation to work with stuff in the binary trees. Okay, so let's do kind of one final goal here of the video. We talked about this in the map class a little bit, right? We didn't have this as an operation, but right, you might want to know, okay, what are all the values we store in a tree, right? How do we kind of look at this stuff kind of for storing things or kind of looking for stuff in that kind of way as well, right? So let me just kind of draw a random tree here. So we have some kind of different values. Remember, we're kind of looking at a binary tree, right? So we always have kind of left and right nodes here. Remember, stuff doesn't need to be kind of exactly balanced or anything here as well, right? So I know all of my nodes are different sizes, so I kind of apologize for that. But if we have some different kind of values here, so maybe we have P, right? We have R, we have X, we have C, we have A, D, and then L and S. So just to be kind of clarifying here, hopefully it's clear. So we have a left and a right node here. The C and the A are children of our R. The X is a child of, or has a child of B on the left. And then B is kind of pointing to the L and the S in this case. So just kind of a random tree here. And we want to print all of these values, right? So at the end of the day, we want to print in some order, right? So let me just kind of clarify that as well, right? The goal, right? In some order, list out P, R, X, C, A, B, L, and S. So that's kind of how we want to think about this here. The ordering I just gave kind of makes sense, right? But in fact, that's not going to be one of them that we talk about here, right? We want to kind of try to take advantage of the kind of recursive nature of our tree definition. So, okay. So all of our kind of tree definitions are kind of thinking of being done recursively. So why is the ordering I'm listing right now not really a recursive way? Because as soon as I kind of go to R, I want to think of that as now a local kind of thing where we're dealing with all the elements of R, right? So as soon as we go to R, we kind of have this subtree we have there. There are ways around this, of course, but we want to kind of do this very, very simply. I'm not going to actually do Python code for these tree traversals, right? This is what it's called when we're working our way throughout all the elements of the tree. But the Python code will be super easy, right? So the hint for kind of the rationale here is we can do these orderings very, very simply with kind of a recursive algorithm then in this case. So there are different ways to do this. If you've heard of the searching things like depth first search, breadth first search, we are not really talking about those now. So I just want to put your mind away from those for the moment. We really want to take advantage of our recursive natures here as well. And these names come from some applications. So we're not going to talk about those too much at the moment, but you can kind of rest assured at least that these names make sense if we're talking about ways we can manipulate the trees and work with the trees in general. So there's kind of three ways to do this. In every single step, there's kind of three components. We visit the current node, and then recursively visit the left tree, and then recursively visit the right tree. And there's three natural orders to do this. Of course, we're kind of always thinking about left coming before right. So ignoring the orderings of those, we can either do the visit root node as the first step, the second step, or the third step. And that gives us these three versions: pre-order, in order, or post order here as well. So those are the kind of different ways we could think about them in this case. Let's specifically here focus on the version here where we're talking about pre-order. So the other ones are fairly straightforward here. I want you guys to practice those, of course. But let's talk about the kind of pre-order stuff here. So step one, visit the root node, right? So we visit the root node here, and so that is visiting P. That will be kind of printing out P or returning P in our list, however we want to do this, right? But kind of if I put a labeling of our listing here on the bottom, right, the first thing that's getting printed out is P in this case. Okay. So that's what we have as our kind of first value here. Now, we recursively, from there, visit the left subtree and the right subtree. So I'm going to kind of highlight these separately here. Of course, this kind of is continuing, right? The hallmark of a lot of recursive things is that you do it recursively, and then you continue doing it recursively. And then maybe you continue doing it recursively, right? So you keep doing this kind of over and over. But the idea is we visited that root node. Now we're going to recursively visit the left subtree and then recursively visit the right subtree. So now if we're focusing on the left subtree, right? So we're focusing on this subtree right here. Well, now we go back to square one. What do we visit first? We visit the root node. So we visit R. Now we're going to recursively visit the left subtree and the right subtree. Well, okay, then we start over. For the left subtree, we have C, and we visit the root node. So we list out the C. There is no right subtree or left subtree for C, right? Once we get to a leaf, we're done. So, right, this is kind of taken care of because in our kind of code anyway, right? What is a left subtree? It's none. What is the right subtree? None. So we have that kind of check. But, right, just to keep this in mind, our recursive stopping point is if you're at a leaf, if you're at a subtree with no children, then you're kind of done, right? You return that root node as that first step, and then you kind of move on. So after the C, we get our first finishing of this recursive left subtree stuff, and then we move to the right subtree to print out A. And so at that point, we've kind of completed the left subtree. And by left subtree, I mean the left subtree of our original root there, right? So we're printing R, then to the left, C, then to the right, A. Now, we're going to do the same type of thing for this other side. We visit the root node, X. Then we visit the left subtree. Okay, for the left subtree, we first visit the root, that's B. Then we visit recursively the left subtree that only has L, so we're done there. We visit the right subtree, it only has S, so we're done there. We visit the right child of X, but there is none, so we're done there, right? And now at this point, we've basically finished our printing or returning of all of the values. We visited all of the nodes in this kind of tree in this case. So all of them are going to be fairly similar, right? In all of these kind of things, right? we do these 3 steps. Visit the root node, recursively visit left, or then recursively visit right. But these things can be done in slightly different orders from there. Okay, so that's just a good thing to kind of know. It's a good way to hammer home again our recursive ideas of trees. There are some applications we can examine with these different orderings as well. But as far as the kind of future is concerned, as far as our next video with this is concerned, right, our next goal is going to be to bring this back to some of our abstract data types before. In particular, we can revisit this map class and kind of think about how can we use a binary tree in terms of implementing a map. So right here we did this introduction to trees. We've seen now of implementation of a binary tree. How can we use this kind of structure to help us do some other kind of different data types or implementations of these data types? That will be the focus of our next video from here. This was Mr. John from Airteam Institute. Thank you guys for watching, and I'll see you next time. Goodbye.